Module 6. Utilizing the Machine Learning Core. In this module, we will capture and tag sensor data via the Python GUI script. We will then use this tagged data in ST's Unico application to create an MLC model. Finally, we will test the MLC model response as we generate real-time shake events. We want to capture sensor data that will be used by the machine learning core to model a shake detection mechanism. Let's start by pressing the reset button on your STWIN.box board. After a few seconds, the green LED will blink intermittently, indicating that the board is ready to capture sensor data. Navigate to the Python examples folder. Type CMD in the File Explorer path bar to open a command prompt. Run the Python HS Datalog GUI application. Click on the drop-down box and choose your board. Click the green Connect button. As in the previous module, we want to disable all the sensors except the SM330 DHCX accelerometer by clicking the green circle to the left of each sensor name. Click on the drop-down box for the ISM330 DHCX accelerometer to display the available sensor configuration options. Human shaking motion is relatively slow, so we can set the output data rate to 26 Hz. The force exerted by a human shake event is also relatively low, so let's set the full-scale range to 2 Gs. We want to tag our event data to distinguish between a shake and non-shake event. Scroll down to Tags Information and click on the drop-down box. Rename the first 2 tag fields to Still and Shake. We will now begin sensor acquisition. Press the green Start Log button to start logging sensor data. You should see the graph on the right populate with the real-time sensor values. Place the board on the table and activate the Still tag. We want to capture approximately 10 seconds of data with the board sitting still on the table. Slowly pick up the board and keep it still in your hand to capture an additional 10 seconds of data. Next, slowly rock the board in your hand for 10 more seconds and then disable the Still tag. Pick up the board and start shaking the board vigorously along one axis. While shaking the board, enable the Shake tag. Capture approximately 10 seconds of data while shaking the board along this axis. Shake the board along a different axis and capture 10 seconds of this motion. Finally, change to the last axis and capture 10 more seconds of shake data. While you are still shaking the board, disable the shake tag. Stop the data acquisition by clicking the Stop Log button. There may be a significant amount of time to wait for the data to be written. Once you see the button turn back to green, the writing process is completed. Click on the Plot Last Acquisition button to view a separate graph of the data you just captured. You can see the period when we left the board still on the table, when we kept it still in our hand, as well as when we rocked the board. We can also see the times when we were shaking the board vigorously. We see that there is a large difference in the peak-to-peak values between the still and shake periods. Close the graph and exit the GUI. In the examples directory, you should see a newly created and time-stamped folder which contains all the information from our capture session. Open the folder and review the acquisition file. You can see information about the current data capture and specifically the still and shake tags that were utilized during the capture. The device config file contains specific sensor state information recorded during the data capture. We can see that all the sensors were disabled except for the STM330DHCX accelerometer. We can also see the enumerated values for the ODR and full-scale settings. The data acquisition file contains the raw sensor data for the capture session. Let's return to the command prompt window and convert this data into a format compatible with the Unico tool. We want to separate this data by our still and shake tags, so we will use the -t option. Type in Python space HS datalog _ to _ Unico dot py space -t followed by your specific capture folder name. The data will now be converted into a Unico-compatible format and saved into a newly created exported folder. Within this folder, you will find the converted still and shake datasets. Open the Unico tool. In the search box, type ISM330DHCX. Several boards will appear, but none of them correspond to the STWIN.box. Uncheck the Communication with the Motherboard option to disable Unico from checking for an attached board. The MLC is specific to the sensor rather than the board, so we can select any of the boards that appear in the text box. Once you click Select, a warning message will pop up letting you know that communication was disabled. You can close this pop-up by clicking on OK. Open the MLC tab on the bottom left. In the Data Patterns tab, click on Browse. Navigate to your converted data folder found in the Python examples directory. Select the still data and load the file. Label the data as still, then click Load. Repeat the same process for the shake data. Label this data as shake, then click Load. Go to the Configuration tab. Our device is the ISM330DHCX, which should be pre-selected from the drop-down menu. Click Next. Set the machine learning core output data rate to 26 Hz to match the input data rate of the accelerometer. Setting a lower ODR will result in the input data being downsampled. Click Next. The MLC can run off the accelerometer, gyro, or other external sensors. For this model, we will be using the accelerometer input only. Set the full scale to 2 Gs and ODR to 26 Hz to align with our capture settings. Click Next. We will use a single decision tree because we are only evaluating shake and still motion events. Click Next. Leave the window length at 52 samples. The decision tree will look at 52 samples or 2 seconds of data to determine whether the board is still or being shaken. Click Next. We can also use the filters on the ISM330DHCX to process the data before running it into the MLC. Since we will not be using any of these filters, select End Filters Configuration and click Next. Now we can see the various features that we can use to classify this motion. We have mean, variance, peak-to-peak, as well as several others. As we saw in the plot of our data, the most distinguishing feature was the peak-to-peak values, so we will select the accelerometer v-squared peak-to-peak as the feature of interest. We can select multiple features if required. Click Next. Now we will select a name for our ARFF or Attribute Relation File format, which will contain all the MLC setting information we just entered. Click Browse and then navigate to the exported folder. We can call this file shake_detection. Save the file. Click Next. We can set the values for the output of the decision tree. These can be set to any value between 0 and 255, but for this exercise, we will leave them as 0 and 4. Click Next. Set the maximum number of nodes for our calculations. Each node is a calculation node. The more complex your motion, the more nodes will be required. Underneath this is the confidence factor. This value can be set between 0.7 and 0.99. If we set too high of a value, we might be overfitting our data to our training set, and we may not get correct results in the real world. If we set this value too low, we might underfit our data and get more false positives. This value can be tweaked depending on your own situation. We are going to leave these settings and then generate the decision tree file. Press the blue Generate button. Details about the decision tree will be printed in the text box below. Click Next. The meta classifier is used to ensure that we have the same calculation value multiple times before setting the MLC output state. Since we are just running a demonstration and the data is not critical, we will leave the meta classifier value set to 0. Click Next. Our configuration is now complete. Let's save the Unico configuration file, or UCF for short. The UCF file will get loaded into the MLC core of the ISM330DHCX device. Click on Browse, then name your file shake_detection. Click on Save. Click Next. A configuration pop-up will appear. Click on OK. Once the file has been saved, exit Unico. Return to the command prompt window. Reset your STWIN.box board. We will run the HS datalog GUI to confirm that our MLC model is working as expected. Connect to the board. Load the previous configuration to ensure our setup is correct. In the Device Config File section, click Load and select the device configuration file from your last data capture. Enable the MLC by selecting the STM330DHCX MLC device. Expand the MLC drop-down box. Browse to the shake detection UCF file and then click the play icon to load it. Start the data logging process. We see that as the board is still, the value of the MLC output is 0. Then, as we shake the board, the output changes to 4, as represented by the red line. When we stop shaking, the MLC output returns to 0. We can repeat this process several times to confirm the accuracy of our MLC. When you are done testing the STWIN.box, stop the log and close the GUI. You can now close all remaining windows. In this module, we captured sensor data using the Python GUI. We then created an MLC shake detection model using the Unico application. Finally, we tested our MLC model in real time using the STWIN.box board. This concludes Module 6.